On September 1st, 1983, Korean Airlines Flight 007 was making a regularly scheduled flight from New York to Seoul, South Korea via Anchorage. Unknown to the pilots, because of an error in setting the autopilot system, the plane began deviating from its intended course and flew over Russian-controlled airspace in Kamchatka. Today, this deviation would have been easily noticeable on the flight's computer GPS system. GPS had been invented a decade earlier, but up until this point, it remained a tightly guarded asset of the US military and wasn't shared with commercial pilots. The autopilot systems of the time followed magnetic courses based on the Earth's electromagnetic field. So far out into the Pacific, away from the ground-based radar stations in Seoul, these magnetic courses would have been the pilot's main navigational guide. The Russians, thinking Flight 007 was an American reconnaissance plane, ordered the plane to be shot down. All 269 souls aboard, including a US congressman, died. Amidst the national outlash, President Ronald Reagan gave civilian access to the global positioning system to prevent future accidents like these from ever occurring again. But this paints an interesting question. If GPS became available to pilots in 1983, how did pilots traverse the globe in the 70 years prior? Be sure to let us know what you think of the video down in the comment section below. It really helps us small channels, and let's jump in. Early planes of the 1910s usually had less than 20 passengers or a few bags of mail. They only flew during the day at a cruising altitude under 3,000 feet and only around 100 miles per hour. At these lower speeds and altitudes, early pilots used a system known as pilotage, literally using points of reference on the ground, like mountains or lakes, to determine their position and their desired course. Going into the 1920s, pilots began flying further, more often, and overnight. As a result, pilots expanded the navigational tools they had at their disposal. At night, it would be impossible to fly by pilotage, since a pilot couldn't see any landmarks. Instead, these early pilots would follow the stars and fly by celestial navigation. Using a tool called a bubble sextant, aircrew looked through an eyepiece and aligned the sextant's crosshairs with a known star, measuring its angle above the horizon. They would take several measurements, and comparing these values to a logbook of the stars determined their position in the sky. Big errors were common due to things like reading incorrect angles at night, turbulence from a bumpy plane, or just shooting the wrong star. After all, on a dark night over the Pacific, there would be literal millions of stars. Over the oceans, they'd also use a tool called a drift sight, a periscope extending from the bottom of a plane. Flying over the ocean, aircrew could look through the drift sight at the waves moving below and calculate the wind speed and direction using simple geometry. The aircraft heading could then be adjusted left or right to keep the plane on the proper course. But the drift sight was only useful at low altitudes during daytime flights. Another technology of the early 1910s was dead reckoning. Dead reckoning was a method of navigation by estimating your current position by using a previously determined position and projecting out your current position based on airspeed, elapsed time, and heading. As you can imagine, the errors from this compound the further out you try to project. But during daytime flights, when you couldn't see the stars, and if there weren't any identifiable landmarks, like if you're flying over a forest or the ocean, this method of guesstimation was the best thing pilots could do. Charles Lindbergh used dead reckoning on his famous non-stop solo flight from the United States to Paris. And there were some more creative navigational schemes before the invention of radio positioning. In the later part of the 1920s, the US government set up a series of navigational guides across the US. Giant cartoon-style arrows stretching in an illuminated path on the ground from New York to San Francisco. This rudimentary form of navigation was part of the Transcontinental Airway System, an effective aid for airmail pilots that, by the 1930s, incorporated 1,500 ground beacons over some 18,000 miles. Every 10 miles, pilots would pass a bright yellow 70-foot concrete arrow on the ground with a 50-foot rotating beacon in the center. These arrows were accompanied with pairs of lights on either side that would flash a code, identifying the beacon's number and thus telling pilots how far along the course they were. The arrows represented a leap forward from previous attempts at lighted guideposts, one of which involved setting huge bonfires next to landing strips to help guide pilots in the night. In the early 30s, the Adock range station came into being. Each Adock range station had 4 130-foot tall towers on the corners of a square layout. The stations emitted unique Morse code signals into each quadrant, and at the intersections of each quadrant, the signals would merge into a steady monotone signal. These radio stations were strategically located across the country. around 200 miles apart, and situated near large airports and along well-traveled air routes. These air routes allowed a pilot to navigate fairly precisely along a narrow path, known as flying the beam. While these towers were effective at helping pilots determine what quadrant they were in, and therefore their rough location, there was no way of determining just from the Morse code signals whether you were flying toward or away from the towers. And it wasn't uncommon for so-called ghost signals to bounce off mountains and falsely lead pilots to their doom. Starting in the 40s, as radio technology advanced, people realized you could use two radio signals emanating from different locations to coordinate your location. This system was known as LORAN, or long-range navigation. LORAN stations manned by the Coast Guard were scattered all across the Pacific, and were the first real high-tech tool used in navigational history. To understand how LORAN worked, imagine you're flying over the beaches of Honolulu with a LORAN receiver. Two stations, one on Guam, the other at San Diego, transmit signals outward at the exact same moment. The signal from San Diego will arrive first, followed milliseconds later by the signal from Guam. The LORAN receiver measures that time difference and could compute a line that would match up with the time differences between these two stations. By doing the same thing with two other stations, you would get another line, and the intersection of those lines would tell you your position. The LORAN system was particularly useful because it relied much less on a pilot's ability to correctly use and interpret the tool, as was common with previous technologies like celestial navigation. The trouble with LORAN was that the signals were in the HF band and very susceptible to interference from electrical storms. So in the midst of a storm, when pilots would need the signal the most, they were often unreadable. In the 50s, we got the VHF omnidirectional radio range, and the military's version, the Tactical Air Navigation System. These are the first pairs of technologies we've discussed that are still widely used in commercial aviation today. These technologies are a bit more complicated than LORAN, but here's the simple version. Whereas LORAN sent out a steady signal for triangulation, VOR emits a modulated signal, which consists of two sine waves which are out of phase. This phase difference allowed pilots to know their bearing, or the direction the plane was pointed. This was the first technology that could tell you both your position and your direction from one measurement. And on top of that, you could tell your position from only one station, whereas with the LORAN system, you need a minimum of 3 stations to triangulate your position. TACAN works similarly, except that it's more accurate due to its use of multiple frequencies to triangulate your position. Both VOR and TACAN are so similar, they're often placed on top of each other to make the FAA's job easier. Then in 1978, the first satellite from the Navstar Global Positioning System was launched. GPS works similarly to the last few technologies, except again a bit more advanced and a bit more precise. The GPS satellites carry very stable atomic clocks that are synchronized with one another and with clocks on the ground. And in the same manner, the satellite locations are known with great precision. Each GPS satellite continually transmits a radio signal containing the current time and data about its position. The time delay between when the satellite transmits a signal and when the receiver receives it is proportional to the distance from the satellite to the receiver. By monitoring several satellites and doing some math, you can coordinate your position anywhere on Earth to within less than 20 feet. At a minimum, 4 of the 24 GPS satellites need to be in view for the receiver to compute its precise location. Today's technology makes air travel much safer and more efficient. But it's easy to see how today's GPS technology is built on the back of decades of advancements in radio telemetry. If you like learning about these aviation technologies, check out this video about clever engineering tricks that have allowed planes to go from this to this. Have a great day, and remember, there is always more to learn.